Okay, so let's look a little bit more at conjugate acid-base pairs, and then we'll talk a bit about ampholytes. So a conjugate acid-base pair, based on the Bronsted-Lowry theory, okay, all acid-base reactions are actually equilibrium reactions. So this is going to become very important later on. We're going to be doing calculations based on equilibrium constants for acids and bases, okay? So these acid-base reactions are equilibrium reactions, and there are two conjugate acid-base pairs. So if you look here at this reaction here, here's hydrogen chloride plus water going to a proton and a chlorine ion. So here is my acid. If we remove the proton, here is its conjugate base, okay? Here is the base, and it accepts a proton, and here is its conjugate acid. So that's why they say there's two pairs. Here's one pair, here's the other pair, okay? So these acid-base reactions are equilibrium reactions, and where the equilibrium lies determines if the system is acidic or basic. So hydrogen chloride and water, this forward reaction, can you see the purple is the forward reaction and the black is the backward reaction? This forward reaction is extremely strong. This is almost complete ionization, so this is a strong acid, okay? Remember we talked about what is a strong acid? A strong acid is when they ionize completely. But then if we mix hydrogen fluoride with water, this one actually doesn't ionize as much. So the forward reaction is just a little small arrow. There's actually not a lot of protons formed. And the backward reaction is much stronger. So if you looked into a solution of hydrogen fluoride and water, you would expect to find far more hydrogen fluoride and a low concentration of hydronium ions. And so then we look at this with water as well. In a couple of slides we're going to look at this with water, but you need to remember that all of these acid-base reactions are equilibrium, and where the equilibrium lies determines if you're mostly acidic or mostly basic. If you are struggling to find a conjugate base for an acid, you take the acid, you remove a proton, and then you've got the conjugate base. If you want the conjugate acid, you add the proton to the base, and then you've got your conjugate acid for the base. You have to always remember when you are adding and subtracting the protons that they have a charge. Do not be giving me compounds with the wrong ionic charge, because I will mark you wrong. So let's have a look at an example of this. An acid donates the proton to give you the conjugate base. Okay, so an acid minus a proton gives you a conjugate base. So look over here, here's hydrochloric acid. Take away the proton, you get a chlorine ion as a conjugate base. Here's nitric acid. Take away the proton, you get a nitrate ion as your conjugate base. Here's sulfuric acid. Remember, this is a polyprotic acid because it's got two protons. So sulfuric acid, take away one proton, you get this ion here, this HSO4 minus ion, I forget its name. And this is the first step in the ionization. Then this HSO4 can lose its second proton and leaves you with its conjugate base of the sulfate ion. And then phosphoric acid does this, and you can actually carry on with phosphoric acid. It's not shown here, but here's phosphoric acid, H3PO4. You lose one proton and you are left with H2PO4. We took away one positive charge, we are left with a negative charge. So that's how you find the conjugate base from the acid. You take away the proton. The base is the opposite according to the theory. The base accepts a proton. So this carbonate ion is a base. Give the carbonate ion a proton and it becomes this bicarbonate ion, HCO3 minus. If you take the bicarbonate ion and you give it another proton, it becomes carbonic acid. So the base is the bicarbonate ion, the conjugated acid is the carbonic acid. If you have a hydroxide ion and you add a proton, you end up with water. So here, the hydroxide ion we know very well is a base, and there water is becoming an acid. Same with ammonia. Ammonia is the base, add a proton, you get the ammonium ion, it's the conjugate acid. Sulfate plus a proton becomes this HSO4 minus ion. Can you see that this one is the reverse of this one? So these two go both ways. This HSO4 ion can lose a proton, and this HSO4 ion can gain a proton as well. So interesting. And that is where we come to this ampholyte. So an ampholyte can either be an acid or a base. If you have an ampholyte and you add acids, the ampholyte acts like a base. If you have an ampholyte and you add a base, the ampholyte acts as an acid. So it can swing both ways. It can pick, do I want to be an acid or do I want to be a base, depending on what you add to it. So water is usually the typical example of this. If you have a look here at this auto-ionization of water, we have two water molecules and they reversibly go to a hydronium ion and a hydroxide ion. So these can go both ways. So here one water has accepted a proton. Here one water has lost a proton. Okay, so the water has done both things. Here's an example with this HCO3, the bicarbonate ion. If we add it to water, it becomes carbonic acid plus a hydroxide ion. Okay, so this water here is acting as an acid because it is donating a proton to this base. Okay, but if you look over here, what you can also do is this same bicarbonate ion with water can then donate a proton to this water. See, this HCO3 minus has got an H over here that can be donated as a proton to the water, leaving you with the carbonate ion and a hydronium ion H3O plus. So these equilibrium reactions will determine whether your solution is acidic or basic, and which is the bossier, acid or base, to push the equilibrium to the left or to the right. But that's why water is an ampholyte. Here's the example of water acting as an acid. Here's the example of water acting as a base, and that is what an ampholyte is. It can either be an acid or a base. So all of the polyprotic acids, so water is the most common ampholyte, but all of the polyprotic acids, they can have steps of their ionization are ampholytes. So here's water. We discussed water a lot. Look at this ion. Here we go. If it donates a proton, it gives you the sulfate ion. But here, if it accepts a proton, it becomes sulfuric acid. So it is an ampholyte. This is phosphoric acid that's lost one proton. So it can still donate a proton and go to this HPO4 minus, or it can go and accept a proton and go back to phosphoric acid. So the polyprotic acids, the first step of the ionization and sometimes the second step for phosphoric acid, can give you ampholytes because they're a polyprotic acid, and then once they've lost one proton, they can either accept it back again and go back to their acid form, or they can lose another one and dissociate completely. Okay, so I hope this makes sense to you, and there we're going to stop again.